And our first speaker for the afternoon is John Geweke. So John is internationally renowned econometrician, and he came to University of Technology, Sydney. We're delighted to have him in Australia as a distinguished research professor in the School of Business in 2009. So John is a chief investigator of the centre, the ARC Centre of Excellence, and he's distinguished for his contributions to econometric theory in time series analysis and Bayesian modelling, and for the application in the field of macroeconomics, finance and microeconomics. He's a fellow of the Econometric Society and of the American Statistical Association, and he's been co-editor on a number of esteemed journals. So I'd like to invite to the stage John.
Okay, well, thank you very much, Carrie, for assembling this. It's I long time ago lost count of the meetings I've been to that you organized, and so my expectations are high as a result, and they're always met. And this is great. Actually, one thing I've learned already today that, for me personally, makes the whole meeting worthwhile. And that is the way in which people are coming to this issue of what I call longitudinal data from a number of different perspectives. And we've all kind of wound up doing rather similar things. So I didn't collaborate or conspire with any of the speakers in the earlier session, but I think it says a lot for the center that this might be one of the themes of the work that we're doing. Now, the work I'm going to talk about today has mainly, over the last, 3 or 4 years, has mostly been motivated by my work with individual clients. So, for example, think about think of the group of the largest delivery organizations in the U.S. Think about very large online retailers. They all face a lot of similar problems, but what has struck me this morning is just how often these kinds of issues come up. And again, personally, I find it best to work in a situation where I understand what the decision problems are that bring me to working with large data. Temperamentally, I'm not well suited to just saying, well, here's a large data set, let's see what we can do, because it's a lot of work. Okay, I like situations where we know what the problem is and should be prepared to be judged on how well we solve those problems in comparison with what's now being done. So I'm going to give a very brief introduction. Then I'll talk about this notion of a hierarchy. And again, we've seen a lot of similar kinds of things today. I'll talk a little bit about this forecasting engine in operation. And then if time permits, I will do a few demonstrations at the end. Okay, so I was trained as an economist, and when I come at this, one of the things I noticed, and everybody else here does too, if you just by living in the economy and society that we do, is economic agents, organizations have a typical kind of structure. In your first economics course, you might learn that, well, a competitive marketplace, prices are set in the market, and so on, and all of that is true. But if you look at the actual organization of economic activity, an awful lot of it is done in non-market settings, right? So a lot of us work within universities, and we know how things are done there. Some of us sometimes chafe at just how non-market this can be. But a lot of organizations will have this hierarchical structure, and I list some examples there. It doesn't make any difference whether it's public sector, private sector, somewhere in between. We've all seen the picture of the organization tree, right? That's the boring thing in the annual report. Well, the fact is that in running an organization like this, right, and running large organizations well is hard, right? And the world is kind of littered with failures of this. One of the things that has to be decided or evolves is to what extent is this going to be centralized and to what extent is it going to be decentralized? Okay, we had a period in the 20th century where we had a couple of goes at an entirely centralized economy. That didn't work too well. In Western societies, we're constantly grappling with the question of which things should be centralized and which should be decentralized. And if you look at what these organizations do, this idea that you would branch tree-like into doing different kinds of things, right? Geography is an obvious example. We saw some of that this morning, and I'm going to do a little bit of that here. But it's not the only kind of thing. So, for example, shippers have different modes of activity, same day, next day, 2-day delivery. What kinds of things should be offered bricks and mortar, which kinds of things online, which kinds of things both. Organization of different product types. All right, some classic examples in economics. Oil refining, right? You can take oil and it can go into a variety of products. Same thing with a financial portfolio. You look at fashion inventory, right? Think of somebody who's in charge of ordering for one of the major retail outlets, okay? These kinds of things come up. Now, it was pointed out this morning that I think it was something, once you get beyond geography, it's not clear how to organize the hierarchy, but even if it's only geography, sometimes that's not so clear either. So, for example, in the U.S., there are these 5-digit postal codes, and the first 2 digits make sense, and then the third one tends to go alphabetically by the name of the area, and then the last 2 make sense again geographically. So if you just do the obvious things with 5-digit zip codes, you can get yourself into a bit of a mess. Once we have different kinds of things, take the issue again of delivery. You've got geography, you've got mode of delivery, you've got day of the year, and so on. There's a real question as to how to organize the hierarchy. Unlike the people who set up the large organizations, as statisticians, we have the luxury of being able to learn from our data, right? If we organize the hierarchy this way, it explains the data better than if we organize the hierarchy the other way, and Bayesians are especially comfortable with using posterior odds to go ahead and do this. And I won't get into any of that today, but a lot of people in this room know how to do this. Whenever we see decision-making, well, it always involves uncertainty in some way, right? Otherwise, what's the big deal? Very often, this involves forecasting, literally, meaning, in time. But it can also be, well, if I create another entity that's a lot like entities we already have, what's going to happen? Again, natural ways for Bayesians to address that. And when we see that the world, in many ways is becoming more and more competitive, okay, and that, in fact, large organization may look like it dominates the marketplace, right? Hard for most of us to remember there was a day, right, when IBM was maybe going to be broken up by the U.S. government because it was clear they were never going to have any competition. And then look at what happened when, PCs came along, right? They kind of caught on late to that. Similarly with other large organizations. DHL might be doing well today, but if they don't do a good job with these decisions, that could disappear. We now have competition among large online retailers, or we could. Some based in the U.S., others based in China, and so on. Now, of course, this question of centralized and decentralized comes up here as well. And we've heard a bit about this today, and this clearly is an essential part of the picture for working with big data. What kinds of things should go in particular places? Where should work with models be done, and so on, and those are important decisions too. One of the points I'm going to make in this talk is that, and you recall I asked a question this morning about forecasting ensembles, is that forecasting is not something where you create forecasts as numbers and you store them someplace, okay? Think about delivery services. In the U.S., there are about 42,000 distinct postal codes just at the 5-digit level, and if we do to and from, right away, we're into a huge number of things. The kinds of things that you want to forecast are specific to the problem. So take the issue of time. What's the time dimension of the data? Well, it depends on what you're trying to do. For a lot of things, daily is sufficient. But if you have a motivating problem, for example, how many servers should we buy for next year in order to handle our peak volume? And peak volume is naturally defined in terms of, at most, a minute long, right? That is, if there's a problem for a minute, maybe you can fix it without creating consequences. And then you ask, well, how many minutes are there next year? It's a lot. How many minutes are there in the historical data? It's a lot. So I think this whole question of how big is the data, there are a lot of data sets out there that go transaction by transaction. The deliverers, they keep their, in the U.S., FedEx, UPS, they keep their data that way. Amazon keeps their data that way. Google keeps their data that way. And for all of these transactions, an enormous number of characteristics. So the number of entities that you might want to forecast is almost incalculable, okay? It depends on the problem. And hence, I'm going to try and move in the little time I have in the direction of, number one, how do you model and use data in a decentralized fashion? And then, how do you handle forecasts as they come in on demand? And we have some examples there. So, for instance, in the U.S., there are all these commercial services where you can go online and you put in one of these 5-digit postal codes, again, over 40,000 of those, and I want hourly forecasts for the next 40 hours. They're there. Temperature, probability of rain, and so on. This is driven by a government organization that does ensemble forecasting. You do the multiplication over 40,000 postal codes times 40 hours, and then somehow you've got to get probabilities of things like precipitation, right? Are those numbers just sitting out there somewhere? Well, no, not at the granularity that people might ask for them. So I'm going to talk here a bit about how do you do that on the fly, right? Nobody is going to sit down and say, well, let me just read over the next 40 hours of precipitation probabilities for all 42,000 postal codes, right? No. They're individuals who want to know about certain areas for particular reasons. Same thing in a large organization, right? Somebody within that organization that I call an internal client here may have a very good reason for needing a particular probabilistic forecast. Inventory, is all about probabilities, and we need to be able to meet that demand in real-time fashion and do it consistently across a number of possible entities whose number is almost incalculable. Okay, so that's why I take ensemble forecasting as an important principle here. I don't know how else to do it, and indeed, the so-called hard scientists have now been at this for quite a long time, and we have quite a bit to go on there. If we think about longitudinal data, what form would an ensemble forecast take? Well, potentially, you've got all of your time units, right? And what are they going to be? Well, it depends on the problem. Everything that might matter to the organization. Okay, so I kind of made up some examples there for UK National Health Service. Obviously, this presents certain challenges in practice. And now on top of that, you're going to do an ensemble. Okay, we're into pretty big numbers now. So what this engine does, and it's something in an early stage, but it is very much beyond proof of concept, is one way to handle this kind of challenge. There are variants on this. I'm sure there are others that probably take a very different approach. So since we're a meeting of statisticians, Before I motivate this, let me stress that the forecasting engine is not about particular models. Okay, the engine is set up in such a way that somebody can plug in a new model, and that is consistent with decentralization, right? There's somebody, 5 levels down in the tree, there is a particular place where they have a unique situation. There's a good forecasting scientist out there, good management, they have experience with that. They're using a model I never heard of. Maybe it's a black box, maybe it's seat of the pants, but if they produced a forecasting ensemble, we can evaluate the thing. As statisticians, though, a nice motivation for this, and when I first started getting into this about 3 years ago, I guess I learned this in grad school somewhere, but if I did, I forgot about it a long time ago, is that, so for discrete data, and that's another interesting thing we saw this morning, I think, a lot of this under these processes, they are discrete, okay? We think discrete, well, you think time, you think Poisson process, okay? And then if you take processes that are independent Poisson, then you add them up, you still have a Poisson process. Now you can go the other way. If you take a Poisson process and you divide it back into its independent pieces, you're going to be using a multinomial distribution, okay? So what does that imply? Well, if I've got a forecasting ensemble that's made one level up, and now I want to divide the thing up among some subunits, what's sometimes called disaggregation, well, a multinomial model would be one example of a way to go. It doesn't have to be that way, but these things are easy to think about. Furthermore, if you use the 2 leading examples that you see in the textbooks, and in my experience, these are, well, they're real problems with Poisson. But given that you have Poisson, that model, right, the Poisson regression is very common. That ties right in with the multinomial logit, okay? These things, there's no change there, okay? It's kind of neat. Poisson regression, multinomial logit model, the way most of it, us learned it, they just fit naturally together. So one of the things this engine is designed to do is in a situation where a lot of work has been put into forecasting at a certain level, and then all of a sudden, because somebody demands it or because of changing market conditions, we need to be able to subdivide this thing across many alternative ways of doing the subdivision. It's not like we have a whole bunch of person-years sitting around to invest in thinking about what these models might be. We would like something that's there on the shelf that can do disaggregation. All of this, of course, taking as given that we have the same underlying database, which, if it's transactions, you probably do. Can be very costly to get it, but it's there. Okay. So an example of this would be in the delivery business. Somewhere down there, they want to have hourly forecasts, sometimes every 5 minutes, of demand in a particular geographical region. Well, and they want it by customer type. Why do they want that? Well, if the delivery van has finished making their scheduled pickups, it doesn't have to start for the airport for another hour. Where should the driver park the van so as to be most likely to give service calls that come in at the last minute from high volume and therefore favored customers, right? No promise that we'll do it the same day, but we would like to be able to meet these last-minute, unpromised calls for pickup if we can possibly do it, okay? And things like that happen all the time. And if we can't bring data to help support these decisions, then it's going to be seat of the pants, and you do enough seat of the pants and competition, and eventually there's bad news. Okay. So as I mentioned, Poisson distribution has a lot of problems. It's under-dispersed. If you've ever worked with this, the literature is full of this, right, on over-dispersion in discrete time series. There is a similar result for the Dirichlet multinomial model. Okay, that should say DMN in that line up there rather than MND. And you get the same kind of aggregation going on. And Dirichlet multinomial simply means that the probabilities are drawn from a Dirichlet distribution. Then once you've got the probabilities, you then go ahead and you get the outcomes in the usual way with a multinomial. You can see right away how this leads to greater dispersion. Okay. The models don't have to be like this, right? If you write down a tree and you've got an allocation mechanism at each node, then you have a model. You don't have to have a deep result like this that says that things aggregate into known kinds of distribution, not when most of the work is being done using simulation technology. Okay. So if you have complete decentralization, okay, what happens is that in each node, right, you have historical data, which I say is a data for itself and all of its children, but if you add up the children, you get the parent, so you really only need the children. It inherits an ensemble of forecasts from the parent, and then these get divided up among the children at the node, okay? So at each node, you have this predictive model for allocating the parent across its children. Okay, now what does this mean? This means that in a decentralized setting, you can say to forecasting scientists, look, here's a form of inputs you're going to be working with, okay? You're going to be saying, and a lot of times a forecasting scientist is responsible for a lot of nodes, okay? You are conditioning on what comes down from above, and then you are producing a distribution of what comes below that over the nodes that are your responsibility. And what you are inheriting comes in the form of an ensemble, and you are then going to produce ensembles as a result, okay? So the only one that's different here is the root node, which has no parent, which, could be the top level of the organization, right? Like, I don't know, how many packages does DHL deliver worldwide? But more commonly, it is something where we have a received method for doing the forecast, and now suddenly we need to be able to disaggregate these things over units that weren't anticipated in the first place. Okay, so there are, as I work on this, I've got two groups of clients, okay? I've got to, it's interesting what autocorrect does. This is supposed to be a forecasting scientist, but notice I've got changed into a foresting scientists, and when you work with machine learners, right, whose first inclination is to use random trees, I think this is kind of a cute autocorrect on the misspelling. Okay. And then ultimately, you have these internal clients, right? These are sort of mid-level, even lower-level managers. They would like to be able to call up a forecast for practically anything they can think of. Why? Because maybe they're responsible for something like, we have to figure out how we are going to staff this distribution center in the week leading up to Christmas, okay? And they need to call out a forecast for that. And these forecasts have to be logically consistent across the entire organization, okay? It was pointed out this morning. If you do this independently, right, you can have financial planners planning for growth of 10% next year, and the people who decide to build the warehouses are planning for 25% growth, and eventually that gets sorted out, but not after causing a lot of trouble for everybody's boss, which nobody wants to have happen. So when I've done this, Spark has become central in working with both client groups. Some of you who may have worked with the R Hadoop interface, which is very nice, but Spark, in the opinion, well, my opinion, but what counts much more is the opinion of people, the data people I work with, just does a much nicer job of this in retrieving the data, setting up what you need at the nodes, and I'll say a bit about that in just a moment. And then, so the idea here is going to be that each node has a relatively small data set that's associated with it. It has a collection of models that's associated with it. And any one node, including both data and models, will easily fit into any laptop that's in this room, okay? So then the trick is, when a forecast is called up, you have things being done independently at nodes, and then things have to be put back together again, okay? Which is still a management exercise, but now we've got something that's manageable, and it's highly asynchronous. Forecasting scientists can keep, you know, their nodes on their server, do their science with the same data that's being used to meet the internal client demands for forecast, and therefore, I run into this all the time. You know, we've always used fill-in name piece of software, okay? So the way the engine is set up is there are a few hooks in that thing. You're basically you've got fields and structures, and as long as your software can put something into the right hook, then you can go ahead and you can use that. Same thing with forecasting methodology. You know, you are not required to be a fill-in name of doctrine from statistics or machine learning. Okay, so basically the way the procedures work on this, and I'll only detail a few here, this thing kind of nicely divides as you go down. What you have up here is intensive in languages and systems that are meant to deal with very large data sets. The second step here is outlining the tree. Okay, so the analysts, which would probably be most of us, are going to say, okay, you know, level one is product type. Level 2 is one-digit zip code in the U.S. Level 3 is delivery mode. Level 4 is two-digit zip code in the U.S. and so on. Obviously, there are many ways this can be done. Obviously, this decision is important. Okay, all hierarchies are not created equal, and likewise, there are alternatives. But again, these are different models. As statisticians, or at least as Bayesian statisticians, we know how to handle very different models. Then there's an editing facility here, and this leads to creation of a full tree structure. So the example I'll show you here is small. It has 4 levels and it has 1,685 nodes, but this scales to much larger trees and many more nodes. Then the Spark comes back in again in populating the tree with the supporting data. Okay, so each node, which has its own local home server, this is where the data gets sent out, and the people I work with, I mean, the time requirements they give using Spark are just phenomenal compared with what they used to take using Hadoop. Then there's model estimation, okay? So model estimation has to scale and be reliable, okay? So a lot of these things are not run by statisticians, okay? You cannot have something that comes to the screen, you know, with probability 10 to the minus fifth that says call your consulting PhD statistician, okay? That has to happen never. Well, how do we meet never? Well, one way to handle this is using Bayesian model combination methods. You assign, essentially, in our language, a log marginal likelihood of minus infinity to a model that doesn't work. And as long as you've got some that do, then you still have a way to go. So that says one aspect of robustness here is, well, there are many reasons for including some simple models, but this is one, okay? But they've all got to execute in real time, okay? And then finally, there's the issue of forecasting on demand, and I will try to show you a little bit of that. So, for example, a tree structure kind of looks like this. Obviously, I'm not going to go through this in detail. It maps back to an original database. Nodes have addresses done in an obvious way by levels. Each one points to where the parent node is, right? So these nodes are just laid out in a great big single dimension vector. Ordering doesn't matter, but it's nice to know where the parent was. It's also nice to know where the children are. There's a name for the model, okay, which tells the software, you know, which model, where's the code that we execute to estimate these things. And then each model has a field here called model specification, and that's entirely specific to the model. The forecasting scientists can structure that however they want, just as they can structure their software however they want, so long as it returns really just a few things to the right parts of the tree. Okay, then populating the tree with data. Okay, that's where Spark gets involved. When I originally started working on this, I said, well, we want to have the original job, which is big, and then we have incremental updates. And, you know, what I've been told is that Spark is so effective, you know, don't write special code for updates. We'll just do it all over again. Then there's model estimation. Okay, so the field for that says, here's how we're going to produce forecasts. Here's the number of simulations, right, or if you like, the number of components in the ensemble. For this particular node, here's the kind of structure that this resulted in. Okay, now this is for different values of the parameters, okay? If you've got a backward model that only has point estimates of parameters, then, you know, you can have just one ensemble for the parameter. You know, we all know the price you pay for doing that. And then certain kinds of metrics that the model can be produced, okay? And basically, if you want your model to be a contestant in model combination, you have to come up with one of these things. And again, to this audience, you know what this looks like. I've written a number of papers about log scores. They do, I think, much more interesting things than any of this stuff or marginal likelihood. Okay. So let me try and, I'm going to close up here by trying to see if we can just do a couple of quick run-throughs on some things here so you can get an idea of what this looks like. Okay, so there's some standard models that come with the forecasting engine. Okay, so one of the things that I found with the software that's out there, and I haven't looked at everything, but I've looked at the obvious statistical packages. This is basically posterior mode stuff. And there was a huge return on having really, really good steepest descent algorithms, okay? That just solved a whole multitude of problems, and the result was software that executed a lot faster. Multinomial logit's completely reliable, no surprise. It's globally concave. But yeah, there's software out there in well-known pieces of software that crashes with the multinomial logit. Then we can with these models in place, we can do both model combination and model comparison. Okay, what do we call this thing? Compare, combine. Okay, so this is looking at the two model structures I showed before. One is Poisson multinomial, the other one's negative binomial, Dirichlet multinomial, okay? And that goes through there, the whole, this is now, we're done with the model comparison for all 1,685 nodes. And what you see down there in the summary statistics, I know it's a little bit hard to read, is that the negative binomial multinomial Dirichlet does a much better job. Okay, these data, which are proprietary, are simply too over-dispersed for multinomial logit to be much of a competitor. And then finally, what I think is the most important part of this idea is that with this structure now and the ensembles behind, the internal client can ask for anything that's a linear combination of nodes, okay? And that's a lot of stuff, especially if you've got this structure set up, you know, with, let's say, like 6, 7 levels. And once you get into that, it's, you know, you almost can't do the math for the forecasts that could be requested, okay? So this is just a little example back here because it illustrates some points. First of all, I keep at the root node, we keep we keep the result. So what this is, well, let's see if I'm in the right direction. Aha, here's the problem. Okay, so at the root, you always keep the forecast at the top level because you're going to need that regardless of what people ask for. And then as you go down the nodes, what you see is, let me blow this up, when you get to the lowest level of this thing, okay, it is these are, right, we're talking about very small numbers of things. They are inherently integers. What you see in all the panels except for the southeast one is you see components of the ensemble, okay? So the black ones, they're data, they're the same everywhere. The red ones are different, okay? This is 90 days going out into the start of a particular year, beginning on January 1. And then one in the lower right here is the mean, okay? Well, you know the mean isn't much of good for anything, right? On the other hand, if I'm asking a question like, if we don't reorder into inventory, which we might do because we're trying to kill a particular area, then what's the date when we're going to run out? Okay, that's a highly nonlinear function, but using forecasting ensembles, it's really trivial arithmetic. And then as you go back up, right, the numbers get larger, okay? And no matter what question you ask, the answers are always going to be logically consistent. That's the beautiful thing about hierarchies. It's also the beautiful thing about ensembles. Basically, any question you can ask. Quantiles are what I think is more important. Solving a real-world decision problem, whereas there is a loss function that you get from engineers and business people whose units are dollars, okay, then you can solve problems like that using the full distribution of the forecasts.
Thanks, John. Any questions? Comments?
Just a comment on terminology. Normally in forecasting, when people talk about ensembles, they mean different forecasts, modeling using different models or different starting points. But you seem to be using it in terms of forecasting or simulating future sample paths. So your examples are future sample paths of the underlying tree. Have I got that right?
Yeah, that's right, and I mean that's motivated by my reading of the meteorology literature, which is the climate modeling literature, which is one of the places this started. I believe they use the word that way. You know, several paths of the future.
Okay. In the interest of time, then, we'll thank John and we'll continue next week. So thank you, John.
Thank you.